I welcome you all for this lecture series on artificial intelligence and machine learning. In this lecture, we'll briefly discuss about the concept support vector that is machine. Support vector machine. So first we'll see the introduction to SVM. SVM stands for support vector machine, and it is a powerful supervised machine learning algorithm used for both classification and regression problem. However, it is more commonly applied to classification tasks. The main objective of the SVM is to find the decision boundary and known as hyperplane that can separate classes in a data set as effectively as possible. By identifying this optimal boundary, SVM helps make accurate predictions on new unseen data. For example, if you have the two-dimensional space like this, we have the positive points one side and negative points one side. It has to perfectly classify positive to negative. So linear classification. The main core concepts of SVM is to find a hyperplane that not only separates the classes in the training data but does so with the largest possible margin. This margin is the distance between the hyperplane and the nearest data points from the each class. These closest points are known as the support vectors, and the entire model depends heavily on them for decision making. And the key component of SVMs are hyperplane, support vectors, and margins. So a decision boundary that separates the data different classes, different classes in feature space. In two-dimensional, it is called as a straight line, and three-dimensional space, it is called as a plane, and higher dimensionals, we are calling it as the hyperplane. And the support vectors means it is the critical data points that lie closest to the hyperplanes. These points are vital because they define the margin of separation. The position and orientation of the hyperplane are directly influenced by support vectors, and removing or altering these can change the decision boundary significantly. And the margin means the margin refers to the distance between the hyperplane and nearest data points from either class, that is positive class or negative class, which are the support vectors. SVM aims to maximize this margin to improve the model's ability to generalize the new data. A larger margin typically indicates the more robust and less overfitted model. And how SVM works? It is based on linear classification and nonlinear classification. Where data can be perfectly separated using straight line or plane, SVM uses the linear hyperplane to distinguish the between the classes. This is called a linear hyperplane, and the algorithm calculates the optimal hyperplane by maximizing the margin between classes while ensuring all data points are correctly classified. And nonlinear classification, if you are going for, in real world classes, data can be separated using straight line in this case. To handle this, SVM employs the kernel trick to map the data into higher dimensional space where the linear separator might exist. In that transformed space, the algorithm can find a hyperplane that separates data which would not be possible in the original input space. And the mathematical equations, if you are considering, and the primary goal of SVM is to find the hyperplane that maximizes the margin between the classes to ensure that model not only classifies the training data correctly but also generalizes well to unseen data. Mathematically, this involves solving an optimization problem that minimizes the norms of the weight vector while ensuring all points are classified correctly. The SVM decision function is expressed as f of x is equal to w into x orientation of the hyperplane, and x is the input feature vector, and b is the bias term. And maximum marginalization is given by, it is calculated by 2 divided by norm of w. This we are going to find out how we are going to get. And there are two types of SVMs, linear SVM and non-linear SVM. And here the the data is linearly separable. SVM finds the straight line, that is 2D or a plane, the best to separate the classes. And non-linear, it uses the kernel function to map the input data into higher dimensional space for better separation. And the SVM kernels are linear kernel. It is there is no transformation is required. It is used to when the data is linearly separable. And polynomial kernel It transforms the data into higher dimensionals using the polynomial function. And another one important kernel is the radial basis function. What do you mean by radial basis function? The kernel, the RBF kernel, also known as the Gaussian kernel. The another name of kernel we can call it as the Gaussian kernel. The transforms the data into an infinite data space. It's particularly effective for data that forms the circular or irregular patterns and is widely used due to its ability to model the complex boundaries. And the sigmoidal kernel, it uses the hyperbolic tangent functions to transform data. It is inspired by neural network and behaves similarly to the activation function used in those models. While not as popular RBF, it can be useful in certain scenarios. And the SVMs for nonlinear data, we are using the technique called the kernel trick. In this case, a method to implicitly map the input data to higher dimensional space computes the dot products of data points in transformed space directly as a using the kernel functions. And if you are taking the example, imagine a data set with the points forming the concentric circle which cannot be separated by a straight line in 2D. Using the kernel trick with an RBF kernel, SVM can project these points into higher dimensional, where a linear separator hyperplane becomes possible, effectively classifying the data correctly. And this is the support vector machine. Here it classifies this block line samples represent the positive samples, and here this represents the negative samples. This SVM is able to classify the positive class into negative class by using the hyperplane, and the support vectors are the closest points to hyperplane from each class. The margin is maximized to ensure that better generalization and accuracy. And here the goal is to find the optimal hyperplane. This is the hyperplane. To separate these two classes, this line should be the maximize the margin between the closest points to both classes. And the support vectors are the critical samples that defines this optimal boundary. And here, see here, this is the this is two-dimensional, this is the three-dimensional. Here the classes are being classified by using the flat surface called, this we can call it as the hyperplane. Flat surface. This hyperplane separates the data points of different classes, just like linear in 2D or plane in the, this is linear. This is linear in 2D, and here we can call it as the plane in the 3D. And here we can classify linear SVM and nonlinear. Linear SVM, perfectly we can classify the positive classes into negative classes. And here the 3D it is a plane. And here nonlinear, so we cannot directly put the straight line. So it will go like this. And this the 3D separation is like this. And here nonlinear, see here, here, these are all the positive point, these are all negative point. So we have to go for put the plane like this by using RBF or some kernel tricks. And here the goal is to maximize the margin, and this separating line should maximize the margin between the two classes. This will see. And here if you are going for infinitely mapping lines, we have to choose any one of the line, each of these lines to technically classify the data correctly. But what is the main goal is we have to select the best line out of all those lines. The best separating line means what? It has to give the it has to maximize the margin between the closest data points of each classes. It is known as the support vectors. And here we can write it mathematically, we can write the equation for each hyperplane. So this is the straight line, the separating line, we can write it as, this function is given by SVM. We begin by separating the hyperplane using the linear function g of x. It is been written W is the weight vector. This W is the weight vector, and X is the input space. B is the bias. See here. So in this case, the positive, if G of X is greater than 0, we can write it as G of X plus W naught is greater than 0. Above classes, hyperplane G of X is greater than 0. And if G of X is less than 0, that means this is the negative points. We'll write it as W transpose X plus W less than 0. So we can write the equation like this: less than 0, greater than 0. And if you are putting the margin nearest to the points, this is already available hyperplane. So here this is H plus, this is H plus, H minus. H plus is parallel to H naught, passing through the nearest to this positive points, and this H minus passing through the nearest to the negative points. Separating margin is the distance between H naught, H plus and H minus. Choose H that has maximizes the margin. So here, if 2 points, if you are taking x1 and x2, we will write it as g of x1 is equal to g of x2 is equal to 0. So we will write the equation like this. So W transpose x1 minus x2 is equal to 0, substituting. And W is orthogonal to, this W is, the weight vector is orthogonal to the vectors x1 and x2. It means W is orthogonal to g of x. This W is orthogonal, perpendicular to g of x. So if you are taking the another plane, and here xp rb, the distance points from the hyperplane of g of x, and xp is the corresponding projection point of x on g of x. Now vector x can be defined by the sum of vectors xp and r. So xp, x is equal to xp plus r. Xp r we can write it as r into w divided by norm of w. And if you are substituting x in g of x, we will write it as w transpose xp r into w transpose plus w naught. So if you are bringing it to the same side, we are getting g of x equal to r into w transpose w divided by norm of w, r is equal to g of x divided by, so this we will write it as g of x divided by w. And distance xp from g of x is equal to 0, g of x is g of x divided by norm of w. So the distance of the origin from g of x is equal to 0 is r naught w transpose 0, w naught divided by norm of w. This is 0, so w naught divided by w. And here h plus, this is nearest to the positive points, and h minus is the nearest to negative points. This we have to find out to maximize. So given the data points less than xi and yi is greater than, where yi belong to positive and negative classes in the label xi, let us replace minus, there is negative by plus 1 and positive by plus 1 and negative by minus 1. So we will write it as w transpose xi plus is greater than 1 for yi is plus 1, and w transpose xi plus w naught is less than 1 for minus 1 for all yi is equal to minus 1. And if you are expressing these two equations, we will write it as yi w transpose xi plus w naught greater than or equal to 1 for all xi. And similarly for if you are bringing in 1 into this side, we are getting this equation, and we will write equation separately. This is for h, and this is for positive class w transpose x, this value, and this is for negative class points, the margin h minus w transpose x plus no, omega naught, that is w naught is equal to minus 1. And margin is given by what? This margin is given by rh plus minus rh minus. So if you are substituting omega, that is w naught minus weight vector naught minus 1 divided by norm of w minus w naught plus 1 norm of w. If you are taking the LCM, these two will be getting cancelled. So we are getting minus 2 divided by norm. We have to take only the absolute value. So in this case, we have to consider the value is margin value is 2 divided by norm of w. And the margin is given by 2w 1 and if you are bringing 2 in this side, we are getting the margin is equal to 1 divided by w norm of w divided by 2. And if in order to maximize 2 divided by, it is equal to minimizing this value, and minimizing norm of w divided by 2 is equal to minimizing w transpose w divided by 2. So this could be explained by the plane. And here this is the optimal function, generalized function w lp is equal to w transpose divided by my summation of 1 to n I 1 to n lambda I yi w transpose xi plus wi minus 1, and lambda there is lambda I is the Lagrange functions. So LP is the W transpose W, the previous equation we are writing over here, and this is the objective function. To this involves the optimizing the parameters. That optimizing parameters was mainly weights and the bias that defines the hyperplane and ensuring the best possible separation between the classes. And these are all the steps used in the SVM pre-processing. It normalizes the data, it handles the missing values or outliers, and the training models are, we have to select the kernels and we have to use the optimization functions. And the model is evaluated by, means the performances are evaluated by using the parameters accuracy, precision, recall, and F1 score. This we'll discuss in the later. And it is more memory efficient. It only supports the vectors are needed for decision making process, and it is robust to overfitting, especially for in the higher dimensional space. Even though it has got lot of advantages, it has disadvantages also. It is computationally expensive, especially for large data set. SVMs can be slow to train. It is not suitable for very large data sets. SVM scale poorly as the number of data points, and its choices of kernel is very difficult. And the applications are, it is used in the text classification, that means a natural language processing, spam or non spam email, image recognition, that is face recognition, handwriting and recognition, and is also used in the bioinformatics, especially for the protein classification, gene expression analysis. And coming into the conclusion, SPM is a powerful algorithm for classification, particularly in high dimensional spaces. It is highly effective when the margin between classes is linear, and it can handle non-linearly separable data through the kernel methods. And it is careful selection of kernels and parameters tuning is important to achieve the performance, optimal performances. So what is the main goal of using the SVMs? We have to find out the perfect hyperplane, that you have to use the concept of margin. We have to find out the value called margin. So hope everyone understood the topic of SVM. The remaining things we'll discuss in the next lecture. Thank you.